Physical pendulums. A physical pendulum is one in which not all of the mass is concentrated at a single point, but rather is distributed in an expanded space relative to the pendulum's center of mass. In simple harmonic motion, we've seen that A is equal to opposite omega squared x several times. What is this equation's rotational analog? Alpha is equal to opposite omega squared theta. The rotational analog of A is alpha. The rotational analog of x is theta. Letter N. The Maclaurin series expansion, which FYI is a Taylor series centered at x equals 0, who cares, is that right there. Okay. Letter O. Approximate the Maclaurin series if x is very, very small. If x is very, very small, then all of these terms pretty much disappear. So if x is very small, sine x is approximately equal to x. Letter P. Here, we're not dealing with x, but with its rotational analog. Rewrite part O, accounting for this fact. Okay, so instead of sine x equals x, we're going to write sine of theta is equal to theta. That's going to come into play here in a little bit. An object of mass m, uniform density, and rotational inertia I is to oscillate about an axis near the top of the object. The straight downward direction is indicated by the dotted line, and the object's axis of symmetry is indicated by the dot and dash line. In the figure, draw and label approximately where the object's center of mass is. All right, well, in an object like this, it's not going to be half of the height, is it? It's going to be down here further, somewhere about right there. Right there is the center of mass, approximately. The distance between the object's center of mass and its rotational axis is usually assigned the variable d. Label this dimension as well as the displacement angle theta. D is going to be that distance right there. That's D. And then theta is this little guy in here. There's theta. All right. Letter S. Determine the net torque that m's weight exerts about the axis of rotation. Torque is force times effective lever arm. The effective lever arm is that little distance right there, which isn't that equal to d sine theta. You check it out for yourself. The lever arm is equal to d sine theta, and the force is m times g. So the net torque is the force, m times g, times the lever arm, which is d sine theta. Letter T. Taking into account part P, and there was part P right there, that the sine of theta was equal to theta, rewrite part S. Well, how can we rewrite this taking into account part P? I think that instead of sine theta, we'll just write theta. So the net torque is going to be equal to m times g times d times theta. This is not d theta. This is not a tiny little theta. This is that length d multiplied by the angle theta. Letter U. Combine Newton's second law in part T. Let's see. Newton's second law. Newton's second law for rotation says that the net torque is equal to the moment of inertia times the angular acceleration. There's the net torque. I believe we were given the moment of inertia. Let's check and make sure. We sure are. Right there in the upper left, we're given I. So I think we can rewrite this as being m times g times d times theta is equal to I times alpha. Moving right along. Circle the correct answers. When theta is that away from equilibrium, the angular acceleration is directed opposite that, isn't that right? And when theta is this away from the equilibrium position, the angular acceleration is directed back that way. I'm seeing a direction one way and then opposite that. A direction one way, opposite that. Letter W. Modify part U, which is right there. We just solved it, but it's on the previous page. Based on part V. Part V says that the displacement theta and the angular acceleration are opposite each other. So we need to put a negative sign on one side or the other. So how about I'll just put it on the left. Negative mg d theta is equal to I alpha. Combine parts M and W and solve for angular frequency. Part M was right there. I just put these here so we don't have to keep flipping between pages. That was part M right there. How can we combine this with that? I'm seeing that they both have alpha. So let's see what we can do here. How about opposite? M G D theta is equal to, let me put the negative sign out front, negative I omega squared theta. All right, that looks right to me. Solve for angular frequency. Well, the negative signs go away. The theta disappears. And what is omega then? It's going to be mg d divided by I square rooted. Letter Y, substitute an equation we derived previously into part X and solve for the period of a physical pendulum. If omega equals that and omega equals that, then we can say, let me rewrite that. 2 pi divided by t is numerically equal to the square root of the whole quantity mgd over I. And if we want to solve that for the period, you check and make sure I'm doing this right. It's going to be 2 pi. And then when we put that on the other side, we've got to flip the numerator with the denominator. There you go. That is for the period of a physical pendulum. And to reiterate, this only holds when the magnitude of theta is small, typically less than 15 degrees. Once you get more than that, then that equation tends to break down.